14.6 hours. That is all it took for one CME from MR 11976 to cross the Sun-to-Earth gap, while the room stayed dark and the fan kept humming above your head. On August 4th, 1972, that near-miss window was razor-thin. The same blast later detonated U.S. Navy magnetic-influenced sea mines off Haiphong, and it did something even stranger on Earth. It pushed currents into power lines, pipelines, and long communication routes across North America. That is the part people miss. This was not just a bright solar event. It was a system test. The storm moved from the sun to military hardware to the kind of wires and grids you depend on every day. And it did it fast. And the timing mattered. Apollo 16 had already flown. Apollo 17 had not yet launched. So the question is not abstract. It is this. If the moon had been occupied that day, how close were we to a very different story? If this kind of warning fascinates you, subscribe and stay with me. And the weird part is that the 1972 solar superstorm near miss left a second footprint on the ground, far from the sun. Off Haiphong, U.S. Navy magnetic influence sea mines went off on their own. And that detail sat buried until Knipp et al. 2018 pulled it back into the light. No smoke in space, no warning siren on the water, just a fast solar udar showing up where it should never have reached. That matters because the same storm was still on its way through Earth's systems. It pushed currents into power lines and pipelines across North America, and long communication lines started acting wrong in the middle of an ordinary day. So now the question gets sharper. If a solar blast can trip mines in one place and shake wires in another, what would it do to a grid built on giant transformers? That is where the 1972 solar superstorm near miss stops being a space story and turns into grid math. When that current gets into long conductors, it does not surge like a normal power spike. It creeps in as a steady push. That is what makes transformer saturation so dangerous. The core stops behaving, the heat rises, and the equipment begins to protect itself by failing. And that is the same basic failure path experts point to in Hydro-Québec in 1989. Different storm, same physics, same weak point. The scary part is how ordinary the setup looks from the outside. A line, a pipeline, a transformer yard, a calm control room. Then the current arrives, and the problem is already inside the system before anyone can see it on a screen. So now the near-miss window feels smaller. If one storm can shake mines, wires, and communications, what happens when it meets the biggest transformers in the network, all at once? And this is where the story climbs off the seafloor and into orbit. The storm hit in the gap between Apollo 16 in April and Apollo 17 in December. That timing is cold comfort. If astronauts had been out on the lunar surface during that burst, they would not have had Earth's magnetic shielding around them. No thick air, no strong natural buffer, just open exposure. That detail changes the scale of the event. A fast solar eruption is not only a problem for hardware, it can become a problem for bodies. For breathing people in suits, walking on gray dust, with sunlight glaring off the ground and nowhere solid to hide in time. So when you hear near miss, do not picture one avoided blackout and move on. Picture 3 layers at once: sea mines off Haiphong, disturbed lines across North America, and a moon mission that, by schedule alone, was lucky. Lucky by months. And if timing was the only shield then, what is the shield now? By the time that radiation threat mattered, the same storm was already pressing harder into the ground systems. Such a current does not look dramatic at first. It rides along long metal paths through power lines and pipelines, and it starts nudging equipment that was never built for a steady push from space. The danger hides so well. With a fast sun-to-Earth transit time, there is no long pause for comfort. The warning is short, the physics is simple, and the weak point is the same one every time: the big hardware at the edge of the grid. That should make you sit up. The 1972 solar superstorm near miss was not just a rare event in old records. It was a live demonstration of how quickly one solar strike can turn into a chain of failures. And the next link is closer than most people think. And this is why the grid warning matters more than the story of the mines. The storm did not need to break every wire to cause trouble. It only had to push a steady current into the long lines and the big transformers, the kind of equipment that hates that kind of load. Once the core saturates, heat builds, and the machine starts slipping out of the job it was built to do. This is the lesson people keep missing when they hear about the 1972 solar superstorm near miss. It is not a one-off curiosity from old files. It is the same physics that showed up again in 1989, when a much smaller storm still knocked out Hydro-Québec in about 90 seconds. So the real question is not whether the sun can hit the grid. It already has. The question is, how many weak points are still waiting in the dark? And which one goes first? So the danger is not the burst itself. It is what the burst leaves behind in the hardware. A near-miss window can look harmless on paper because the lines are still standing and the lights are still on. But that steady current is already inside the system, and transformer saturation can start before anyone outside the control room notices a thing. That is why the 2018 analysis matters. It showed the mines, the wires, and the grid were not separate stories. They were one chain, with the sun at the start and human infrastructure at the end. And once you see that chain, the question changes. Could this happen? It did. The real question is which part of the network would feel it first if the timing were only a little different. And that is where the risk gets ugly, because the weak point is not one wire, it is the whole long path. A long conductor gives a geomagnetically induced current somewhere to go. If the line is stretched far enough, the current does not need to be huge to matter. It only has to sit there long enough to push the transformer toward saturation. That is why engineers keep circling back to the same fear. The 1972 solar superstorm near miss was fast enough to matter, and fast solar weather gives less room to react than people assume. You do not get a slow build. You get a brief warning, then the load lands. And once the load lands, the grid does not fail as one neat blackout. It starts at the edges, in the places that look ordinary right up until they do not. So if the first weak point is not the line but the transformer, what happens when the line keeps feeding it anyway? That is why Hydro-Québec keeps coming back into the picture. In 1989, a smaller storm still shoved the grid into collapse in about 90 seconds, which means the failure mode is not theoretical. When a geomagnetically induced current gets into a long line, it does not need to be huge to matter. It just needs time. It keeps pushing until the transformer starts to lose control. And then the problem moves from the wire to the equipment itself. That is the comparison that makes the 1972 solar superstorm near miss so unsettling. If a weaker event could drop a major power system that fast, then the stronger one was already in the right class to do worse. Already. And once you see that, the next question is obvious. What part of the network would fail first if the storm arrived on a weekday, with demand already high? That is why the 1989 blackout keeps hanging over this story. It was weaker, and still the grid buckled in about 90 seconds. A geomagnetically induced current does not announce itself with a bang. It creeps through long lines, and the transformer only tells you it is in trouble when the heat is already there. By then, the control room is not seeing a theory. It is watching a live failure. So when people ask what a fast solar hit would do now, the answer is not maybe a few lights out. It is a chain. First the line, then the equipment, then the bigger system built on both. And that is the part that makes the 1972 solar superstorm near miss hard to dismiss. The sun did not just miss us by a little. It showed the root. The next question is the ugly one. If the root is already known, what exactly stops the same current from choosing a different target? What stops it, in theory, is speed of response. And that is exactly where this story gets uncomfortable. A fast sun-to-Earth transit time does not leave much room for debate, meetings, or second guesses. The signal comes in, operators have to decide, and the system they are trying to protect is already carrying the same long lines and heavy equipment that proved vulnerable in 1972. And remember, this was not only a grid problem. It disturbed long-distance communications across North America and pushed current into pipelines too. That matters because a modern society does not fail in one clean step. Power, communication, transport, timing, they lean on each other. So when people imagine resilience, they often picture backup plans. But backup plans also depend on lines, signals, and hardware staying stable long enough to use them. That is the trap. The storm does not need to destroy everything. It only needs to hit the connection points first. And those are exactly the parts we trust most. And the moment those connection points wobble, the problem stops being technical and starts becoming social. You lose one line, and maybe another line carries the load. You lose communications at the same time, and the response slows. You push current into pipelines while the grid is already under stress, and now separate systems are all dealing with the same sky-driven pressure. That is what makes this event so hard to file away as old history. The 1972 solar superstorm near miss linked things people normally think of as separate: military hardware near Haiphong, communications across North America, pipelines, power equipment, even the safety of a lunar crew if the calendar had shifted. So when you ask what resilience means, you can not only ask whether a transformer survives. You have to ask whether the systems around it can keep working while decisions are being made under a very short clock. And short clocks are where human confidence usually starts to crack. That is where the argument stops being about physics and becomes about power, money, and delay. Everyone can agree the grid is vulnerable. The problem is that protecting it means choosing which equipment gets hardened first, who pays for it, and how long the work takes while the sun keeps moving on its own schedule. That is the slow part, and the storm is not slow. So the 1972 solar superstorm near miss sits in this awkward place, old enough to study, close enough to scare engineers, and still not enough to force the whole system to move at the same speed. You can map the risk, write the reports, and still leave the weak points waiting. And that is the question now. If the warning is known, the failure mode is known, and the clock is still ticking, what exactly has to happen before action finally beats delay? And that crack usually appears in the same place, the moment warning turns into choice. A fast event does not care whether one operator wants more data, whether one agency is waiting for confirmation, or whether one utility thinks the risk is overblown. The current is already moving. The lines are already exposed. The equipment is already doing exactly what physics tells it to do. That is the ugly advantage this kind of storm has over any human system. It arrives as one event, but it hits a world divided into separate owners, separate procedures, separate assumptions. Power operators think about transformers. Communications crews think about signal loss. Pipeline managers watch their own instruments. Meanwhile, the same sky is pressing on all of them at once. So when people say, "we'd handle it," I always want to ask one thing. Handle which part first? Because the first decision is not made after the failure begins. It is made while everything still looks normal. That's why the hard part is not knowing the risk. It is acting before the room fills with doubt. The Sun-to-Earth transit time was short enough that nobody gets the luxury of a long briefing. A geomagnetically induced current does not wait for consensus. It keeps pressing through the same long lines while people are still trying to decide who is responsible. And that is where the 1972 solar superstorm near miss stays useful as a warning. It shows you what happens when the signal is clear, the hazard is known, and the system still moves at human speed. The question now is not whether the next storm will find weak points. It will. The question is whether the first alarm reaches the people who can still shut anything down, or whether the clock runs out first. And if the clock runs out first, the failure does not stay politely inside one control room. A geomagnetically induced current pushes into long lines. The stressed equipment begins to misbehave, and the first loss is not just electrical. Communication links were already disrupted across North America in 1972. Pipelines were already feeling it. That means the same event can damage your ability to see the problem, talk about the problem, and isolate the problem at the same time. That is why this kind of storm is so dangerous. Not because every system fails instantly, but because the systems that are supposed to support each other start slipping together. One weak signal, one delayed decision, one overloaded transformer, and the margin gets thinner very fast. So when people imagine a crisis, they picture the moment after the lights go out. This is worse. The critical moment may come a little earlier, while the screen is still glowing, the radios are still crackling, and someone has to decide whether to shut parts of the network down before the storm makes that choice for them. So the warning is not just scientific, it is operational. You can know about the storm, know about the wiring, know about transformer saturation, and still lose time because the response has to move through people, not equations. One phone call, one order, one hesitation. That is all it takes for a fast solar hit to keep pushing while the grid is still waiting for permission. That is the part the 1972 event exposes so cleanly. The threat was real, the physics was real, and the delay was human. And that leaves one final problem hanging there. If the next one arrives with the same short clock, who is actually the first person to act? In the end, nothing heroic stopped it. The storm passed, the wires cooled, and the only reason you can study it now is that the damage never got the last turn. But the sharpest image is still the same. A fast burst, crossing the Sun-to-Earth gap, then finding sea mines off Haiphong, long lines in North America, and a lunar mission window that had not opened yet. The lesson is sitting inside that chain, in timing. A storm like that does not wait for perfect plans. It only asks whether the system can move before the current gets there. And the room around that fact is quiet now. A page turns. A breaker stays open. Somewhere, a transformer hums on under a pale morning sky. If you want more documentaries like this, clear, tense, and built on real science, subscribe and stay with me.